Today I'm going to talk about several topics related to low-level hardware design because in many ways that relates to the other things that we talked about earlier this semester. So first topic is, as I'm sure you're all aware, digital logic circuits are actually built using analog circuits. And so the signals that are sent and received between gates are, analog values. They can either be voltage values if you're using voltage mode logic, or they can be currents if you're using current mode logic. Virtually all digital logic these days is voltage mode logic, but it is possible to create circuit mode logic. In fact, circuit mode logic has some advantages over voltage mode, but the big advantage that voltage mode has is power efficiency or energy efficiency. So in voltage mode, you have to have basically voltages that represent 0 and 1, the digital signal values. So the problem that you have there, though, is when you have a logic gate that's sending an output to another logic gate, those connections will be subject to noise, which comes from mainly wire resistance. So this wire has resistance, so you'll get a voltage drop between the driver and the receiver. But there's also power supply noise, and which comes from power supply fluctuations from the digital circuit switching. And the only way to deal with that is using capacitors. You can put decoupling capacitors on the chip to try to filter out that noise, but you can't, you can't eliminate it entirely. Digital circuits are kind of noisy in that sense. And then there's also crosstalk, which is where you have capacitive coupling between wires that are near each other, right? So these are all sources of noise that's going to change the value between the driver and the receiving gate, right? So what ends up happening is that even though you expect the voltage levels to be basically, 0 for, ground, 0 volts for the value 0, and VDD, which is the power supply, for value 1, that's almost never the case because of this noise, right? So, so that leads us to this thing called the static discipline that says that when you generate circuits, if you're giving valid inputs to a circuit, and by circuit I mean potentially a digital logic circuit with multiple gates. If you're providing valid inputs, you should get valid outputs, right? And so for that, in order to make that guarantee, you have to consider this concept of noise margin. So the idea is that with these logic gates, there's ideally, 0 is ground, 0 volts. But there's this notion of VIL, voltage input low, which is the highest voltage you can have and have it still be counted as a 0, right? So it's the maximum voltage that's considered a logic 0, right? For the input of a gate. And then likewise, there's the same concept, but it's applied to the output of the gate. So that's called VOL, voltage output low, right? So, you might ask, well, why is it different? Well, the difference is because what we showed here, which is where you have this output, basically a range of output values is going to be different from the range of input values because of the noise. So you have to separately consider the input and the output threshold value. So again, the maximum output voltage that's considered a 0 is VIL, and then the maximum of output voltage that's a 0 would be VOL, V output high. VOL, V output low, right? Likewise, the minimum voltage that's still considered a 1. Now remember that a 1 is, you generally think that that's the power supply, right? The voltage, whatever your power supply voltage is. But, you can go under your power supply voltage and have it still count as a 1. And so the minimum output voltage that's still considered a 1 is VOH, voltage output high. And the minimum input voltage that's still considered a 1 is V input high, right? Okay? So ideally, if you have a buffer, so this is a buffer gate where it's basically the input, whatever, the output is whatever the input is, right? And this could also be an inverter or an AND gate, but this is kind of the simplest kind of gate. So input is A and the output is Y. So in a perfect world, the threshold between 0 and 1 on the input would be VDD divided by 2, right? So if it's, let's say you're at 2 volts power supply, then anything below half of that, which is 1 volt, would be a 0. Anything above that, half of that would be a 1, right? And then that would be for the input, and then the output would always just be 0 or VDD, right? So in other words, this conceptual gate, anything in the lower half is considered a 0 and causes the gate to be, boom, 0. Anything above halfway is considered an input of 1 and causes the output to just go straight to 1, right? And so, so that would mean that the VIL is VDD over 2, and the VOL is just 0, right? Because, if you have an output of 0, it's just going to be 0 volts. And so you can calculate the noise margin is going to be the difference between the input low and the output low, right? So in other words, if you have 2 of these buffers connected to one another, you can actually hit that intermediate line, that intermediate wire, with up to VDD over 2 volts of noise, and it won't cause any problems, right? So that's the noise margin, right? And then for the high, it's the same thing. V input high is VDD over 2. V output high is VDD. And so the noise margin there is the difference between those two. Now, one of the things that's a little confusing here is that you'll notice that the noise margin for, that's a typo, sorry. There's a typo there. There we go. Noise margin, I screwed that up. Noise margin high, sorry. I'm sorry, I'm not in equation mode. This would be V, oops, sorry, typo. So this should be V noise margin high. And this would be V noise margin low. That's the problem. There we go. Sorry. Right. Okay. Yeah. Sorry. There, I fixed it. Okay. So the noise margin low is going to be VDD over 2 minus 0. Noise margin high is VDD minus VDD over 2. So when you take these differences, you have to swap them. So for the low, it's input minus output. And for the high, it's output minus input. So it's a little confusing. But basically, in both cases, your noise margin is VDD over 2, which is good. That means you can hit that intermediate wire with a lot of noise. The problem is that that's not how real gates work. So if you look at the curve between, so in this case, this is the horizontal axis is the input voltage, and the vertical axis is the output voltage. So what ends up happening here is that as you start to increase the input voltage, the output voltage kind of creeps along a little bit, right? It creeps along slower than the rate at which you're increasing the input, right? So I'm increasing the input. It kind of just it barely goes up. And then at some point, you're going to hit a magic number. You're going to hit the transistor threshold voltage, right? And at that point, it's going to zoom up really fast, right? And then after it zooms up, it sort of levels out, So this is the threshold, but in this, for the sake of this discussion, this is the VIL, right? So this is the input low, right? That's the point at which this happens, right? So when I hit the input low, the highest input that's considered zero, logic zero, at that point you're going to see what's called the unity gain. Unity gain is when the slope, so the slope is like less than 1, less than 1, less than 1. The slope will eventually hit 1, and then it will become much greater than 1, right? So the unity gain is at the point at which the slope of that line becomes 1, right? And that's the point where things take a drastic turn, right? Okay, now, if you look at the point on the output voltage where that happens, that's the VOL. So the VIL is going to be around, I mean, it depends on the technology, but let's just say, you know, this might happen around 700 millivolts, right? 0.7 volts. And then, you know, the transistors kind of become unlocked, and then you'll get this unity gain. But at that, right at that unity gain, the output voltage is still pretty low. It's lower than 700 millivolts, right? This might be 100 millivolts or less, right? So you can see where this is going is that I can be much higher here on the input than my lowest output voltage for a 0, right? And then the same thing happens at the top. As I continue to increase the input voltage, there'll be another unity gain point at the input VIH, right? The lowest input voltage that counts as a high, logic high. And then, and then it will sort of, you know, and it'll sort of level out, right? And so the point at that second unity gain point is the VIH for the input, and the corresponding output is VOH. You see? So you can see that because VIL is greater than VOL, what's happening is that this gate is kind of protecting you a little bit in terms of the noise on the intermediate wire, right? It's more tolerant of higher inputs for 0 or lower inputs for 1, right, than it is the way that it actually puts a value out. Does that make sense? Right? So, in other words, if you calculate the difference between these, so the difference between the VIL, and in VOL, right, is your noise margin for low, NML. NML. I guess there isn't a V there. Oh, so NL, noise margin low, right? And then likewise, the difference between VOH and VIH is your noise margin high, which means that if you look at the gate, you should never, hopefully, you never have an input voltage that's in between VIL and VIH. That's called the forbidden zone, right? You don't want to be there because that's the point between the two unity gain points where you kind of have, you know, this, you know, where you basically have an amplifier, right, instead of a gate, right? So you don't want the input to be in the forbidden zone. And as long as the input is not in the forbidden zone, then your outputs will also likewise never be between VOL and VOH, right? So anyway, that defines that basically limits or puts a limit on how much noise you can subject to these wires in a logic circuit. And this just shows the same thing again. So yeah, so the noise margin high is the VOH minus VIH. Noise margin low is VIL minus VOL. And again, I just want to point out that, you know, the input side is swapped, right, depending on if you're high or low, you know, when you take the difference, right? Okay, any questions about that? Okay, so here's some, this is from the textbook. They have some numbers for this. So they have these like different logic families. You might have heard of TTL logic, transistor to transistor logic, CMOS, low voltage CMOS. These are names given to logic, families, ways to, technology. And each one of these, you can see that over time, it's not shown here, but it's implied that this is older technology at the top of the table, and there's newer technology at the bottom of the table. What's happening is, the voltage levels are tending to be reduced. They keep going down. So back in the 70s, digital logic circuits ran at 5 volts. Nowadays, they run at like 1, I think, or maybe even less than 1. That's the VDD, that's the power supply. And then for these different logic families, you'll have different, VIL, VIH, right? So for low voltage CMOS, which is a 3.3 volt, it's kind of like what you'd have like with an Arduino, right? 3.3 volts. VIL is about 0.9, right? That seems kind of high, actually. But that means that anything below 900 millivolts is a 0 on the input of a gate. And then likewise, VIH, anything above 1.8 is considered a 1, right? And so the forbidden zone would be between 0.9 and 1.8, right? And then likewise, VOL is 0.36 and 2.7. So the VOL and VOH is obviously it's a wider range because basically because the gate is kind of cleaning up the noise for you a little bit, essentially, is what's happening there. Okay, so next topic is semiconductors. So digital logic chips are made out of silicon. I'm sure you all know that. There are other chips, though. There are other technologies besides silicon. There's gallium nitride, gallium arsenide, silicon carbide. There's other semiconductor technologies. However, those are not used for digital logic. All digital logic is made with silicon. Those other technologies are used for LEDs, radar, other optoelectronics, that kind of stuff. So silicon is an atom, right? And it's in the column on the periodic table, column 4. That means it has 4 valence electrons, 4 electrons in the outer shell. And silicon, I think, is it's one of, if not the most abundant element on Earth. So it's very common. Except when you find it in nature, it's usually in the form of silicon dioxide, which is glass, right? It's not pure silicon. Pure silicon is actually kind of difficult to manufacture. The way they do it is they grow pure silicon into a crystal. It forms a crystal. It forms a crystal lattice. And so what happens in that pure silicon crystal lattice is each silicon atom forms covalent bonds with 4 neighboring atoms. Okay, and it creates this really kind of neat repeating structure. So if you look at the angles, the bond angles, basically the angle of each silicon atom relative to the others, those angles are repeated, and the smallest unit of repetition is called the unit cell. And a silicon unit cell, I don't remember how many atoms there are. It's shown there, but 1, 2, 3. I forget. There's a certain number of atoms in the unit cell for silicon. And the cell itself is 5 nanometers. 14?
Because element number is 14.
Yeah, it could be. But anyway, the size of the cell is 5 nanometers, right? So the cell is a square. You can capture the cell in a cube, or I should say a cube, right? And the cube, each side of the cube is 5 nanometers, right? Now, the reason I bring this up is because I'm sure you know that modern chips can be fabricated with a feature size of what they claim is 4 nanometers, right? Which means that technically they're making chips that have features that are smaller than the unit cell of silicon, right? Now, are they really doing that? No, that's a lie, as it turns out. The fabrication technology, when they say when they say Intel has unveiled its 4 nanometer process, what they really mean is that it's equivalent to 4 nanometers, but it's not actually 4 nanometers. The reason they call it, it's bigger than 4 nanometers, but they create this 3-dimensional structure called a FinFET that gives it properties that would be equivalent to a 4 nanometer gate, right? Now, the spacing between the atoms is actually about 0.5 nanometer, right? So, when people talk about like Moore's law ending, that's true because there is a physical, silicon atoms will form these structures, and the sizes are, these are the sizes. You can't make anything smaller than that, obviously, right? But when you create these crystals, you grow the crystals. These are a semiconductor because they basically don't conduct any electricity. But what you can do, what was discovered, is that you can dope them, meaning that you can basically you can heat up the silicon, and then you can fill a chamber up with gaseous element that gets injected into the silicon lattice. And what ends up happening is called doping. And what ends up happening is some of the atoms, the dopant atoms, actually replace some of the silicon atoms in the lattice, right? Now, you can dope it more or you can dope it less. You can heavily dope, in which case you replace a lot of silicon atoms, or you can lightly dope, in which case you replace less. But the point is that what you're doing is the dopant atom that you put in there either has 5 valence electrons, meaning it's from 5, column 5, right? Or it has 3 valence electrons, meaning that it's from column 3, right? If you dope it with column 5, what ends up happening is that, like for example, if you take boron, let's look at arsenic. Arsenic. If you take arsenic and you stick it in there, the arsenic has an extra electron, right? It has 5 valence electrons. And that electron has the ability to move, it can leave the arsenic atom. So the arsenic atom has 5 valence electrons, but that extra electron can leave. And it can actually, it can just piece out, and it can move around the lattice freely. So what happens there is that you have what's called mobility, and that extra electron, it can just leave the arsenic atom, leave it with only 4 valence electrons, and it can move across these silicon atoms, and that becomes a charge carrier. And that allows current to be, it allows the new doped silicon to be a conductor, right? Likewise, if you put in a boron is from group 3, this has 3 valence electrons, and this one is kind of trippy, but what happens here is that the boron has what's called a hole. It's a lack of an electron. And that hole, it's like an empty spot where an electron could be. That hole is also mobile, right? It can move around, and that can also be a charge carrier. So if you have extra electrons, meaning you got a 5 dopant, then that becomes a negative N-type silicon, N-dope, right? And if you have a hole, then it's P-type, positive charge carrier, right? So charge carriers are just a way for current to be. So for example, if air is not a conductor, but if I hold up 2 pieces of wire and I put a very high voltage between them and I start putting them closer together, eventually you'll get an arc, between the two. And what that arc is when the air between the 2 electrons becomes ionized, and the ions in the air become the charge carriers. That's what an electrical arc is. That's really the same thing that happens in the silicon, except instead of an arc, it's these charge carriers that are moving around, right? Does that make sense? So that's basically how that works. But Um, this is the part that's kind of strange, though. So, well, a couple things I want to note. Arsenic is a poison. That's a poison. And you certainly don't want to be around arsenic when it's vaporized, because that's real scary, right? That's why they don't make chips in the United States. Americans are scared of that, vaporized arsenic. Not only that, but part of the manufacturing process is you have to use this technique called photolithography to create layers on the chip. And that involves using something called piranha etch acid, which is the strongest acid on Earth. It'll like dissolve your hand in a second if you touch it. So very dangerous stuff. That's why we don't make chips in the United States. Americans too afraid of that. But the other weird thing that's happening here is that when you put positive, you put the hole, right? You dope it with a hole. Those holes are known as the majority carriers. And this is the part that you kind of have to, it's almost hard to believe. But the holes are the majority charge carriers. So if you just try to send current through it, the current is sent through with the majority carriers. However, you also get minority carriers that are the opposite polarity. So if I put holes in my silicon, I'll also have electrons in there as well, except the holes are more prevalent inside the lattice. But both of them are mobile. They can move. They got mobility, right? Okay? So keep that in mind. P-type has holes, but those are the majority carriers. There's also minority, which is the opposite type. And so that's how a diode works. A diode is when you take a P-type and an N-type silicon and you mash them together. And if you put a positive voltage on the P-type with respect to the N-type, okay, what'll happen is, what happened there is if you've got a positive voltage, P relative to N, what that will do is it will attract the minority carriers from the, it'll attract the minority carriers, the holes, the electrons over here in the N-type, and the holes in the P-type will come together, right? And this will allow you to pass current from the P-type to the N-type across this junction here, right? This is called, forward bias, right? But the problem is if you apply a voltage on the N-type relative to the P-type, right? The positive voltage here will push these majority carriers away from the junction, right? So you have positive here, it'll push these holes away. And what'll happen is the charge carriers will move away from the junction, and you can't send current, backwards. It won't allow you to send current the opposite way, right? So that's a diode. Now the diodes are not very useful for logic, but you can make this structure called there's different types of ways to use semiconductors to make transistors. One way to do it is this thing, the type that's used now is metal oxide silicon MOS transistors. So this is, what happens here is you basically have N and P type silicon. The P type is now this is a cutaway view. This is like looking at it like a sandwich. Like you have a sandwich and you cut the sandwich in half and then you look at the side of the sandwich, right? This is a cross-sectional view. What's happening here is you have a P-type silicon and then you have two islands of N-type silicon that are close to one another. And they're separated by a little bit of space. That little bit of space is what they refer to when they say that Intel has come out with a 4 nanometer process. This space is supposed to be the minimal amount of space possible. It's also known as the minimum feature size. This is the smallest feature you can make when you're fabricating the chip, is the space between these two islands, right? And the way this happens is this silicon is doped for P, right? So you take boron and you blast the boron in there, right? First you grow the silicon, then you blast it with boron. But then you take your arsenic and you blast arsenic into these two islands. And what happens is if you already have P-type silicon, but you start doping it as N-type, it'll reverse the doping, right? It'll actually go from P-type back to N-type. Well, I shouldn't say back to N-type, but it'll transition it, right? So I started out with boron atoms in here, and then I hit it with the arsenic, and I can create these two little islands of N-type, N-type and inside of a P-type lake or substrate, right? Surface. So then you end up with diodes here. So if you ground the substrate, you ground it, make sure that this is electrically grounded, then you're guaranteed to always have a reverse bias. You won't ever have any current go between these two guys, right? Because this is a diode and this guy's at ground. So you're basically, by grounding the substrate, you guarantee that you're always reverse biased on these two islands. So these two islands are electrically isolated from their substrate, even though they're touching one another, right? But they're not connected electrically, right? Then you create a capacitor between the area between these two guys, these two islands, is called the channel. You create a capacitor. In other words, you put another thing above it with a layer of glass in between. This thing in between is called is silicon dioxide, which is that's not even a semiconductor. That's just a straight up insulator, silicon dioxide, right? Glass doesn't conduct electricity at all, unlike pure silicon, which conducts it a little bit with high resistance, right? So this is just a capacitor, right? Now, in the old days, the top of this capacitor was made out of metal. That's why it's called metal oxide semiconductor. Metal is the top, oxide is the middle, semiconductor. This is talking about this little middle region, which is what they named the technology after, when they say, 180 nanometer process, right? Right, so but now they don't use metal. They stopped using metal for that a long time ago. Now they use something called polysilicon, which is, it's silicon that's highly doped. It's what they make solar panels out of, polysilicon, solar panel material. Why did they switch from metal to poly? I don't know. It worked better somehow, right? So what ends up happening here is that this top of this capacitor becomes the gate. And so if I put a voltage on this gate, what will happen is, remember I told you that in the P, you've got holes, right? Lack of an electron, so it's positive charge carriers. But there's also, but those are the majority carrier. There's also minority carriers. There's some electrons in there too, but they're real hard to find. They're very, very rare, sparse. They're very sparse. But if you put a voltage on that gate, or actually if you charge the gate more accurately, right, because it's a capacitor. So if you charge the gate, it will attract the minority carriers out of this P-type substrate, and it'll create, so remember that, so the substrate is grounded and it's P-type, so we got a bunch of plus carriers. So if we charge up that gate, it actually attracts the minority carriers. So even though it's P-type silicon, it still has some electrons in the lattice that can serve as charge carriers, but you can only find them if you put a charge on the gate, on the capacitor, right? So that will attract those electrons, and the electrons will actually create a bridge. It'll make the transistor look like this is N-doped and this is N-doped, and the little area under here is also N-doped, even though it's part of a P-doped silicon, but you've attracted the electrons there. It creates a channel of charge carriers, and that way you can start conducting between these two islands, which are called the source and the drain. Right? Does that make sense? So those minority carriers are always there, but they're real hard to find unless you get them up in there. Now, what ends up happening, though, there's really interesting, because when this happens, the channel, even though it's part of the substrate, actually becomes disengaged, disconnected from the rest of the bulk, the substrate. So this channel, so like I mentioned that, the substrate is grounded. You want to ground the substrate to create a reverse bias diode. Basically, you don't want these two islands to be connected to the substrate. So you ground the substrate. But when you charge this capacitor and you create charge carriers to the channel, those charge carriers are not electrically connected to ground, to the substrate. They're completely separate. Does it make sense? Just because they're, you basically, they separate, right? You attract these minority carriers, but at the same time you repel the majority carriers away from that channel, right? Now, why do I bring this up? Why is this important? The problem is when you charge a capacitor, there's two plates on a capacitor, right? And in order to charge a capacitor, there has to be a voltage difference between the two plates, right? So if this is the first plate and this is the second plate, I know what the voltage of this top plate is because that's the gate. I'm driving that with a signal of some kind, right? But what is the voltage of the channel? I mean, it's not ground because, as I mentioned, it's disengaged from the ground, disconnected from the ground, right? What is the voltage of the channel? Well, the voltage of the channel can only be calculated as a gradient of voltage from the source to the drain. So basically, the left side of the channel is basically the source voltage, right? The right side of the channel by the drain is basically the drain voltage. And so there's a gradient of voltages. The voltage is high here. Well, it's basically there's an average voltage, which is the average of this and this, right? That's the average voltage. But the voltage at each point in this channel is different, right? Depending on the source and drain, right? So you end up with a gradient of voltages there, right? Now, the problem is that if this transistor has a very high voltage difference between its source and drain, this weird thing happens where let's say the source is really low and the drain is high, the capacitor you'll have a different potential along this channel relative to the gate, right? And if the voltage difference between the source and drain is high enough, it'll actually pinch off the channel. But I'll talk more about that in a minute, but just keep that in mind. So in this case, this is called an NMOS. Why is it called an NMOS? Because, why would you call this an NMOS? There's P and N, right? Because the source and the drain is the N. So the transistor is named after the dopant used for the source and drain, right? You don't name it after the dopant that's the body, which is the substrate, which is the channel, right? Okay, so that's an N-type. So basically, an N-type transistor will turn on, meaning that it will electrically connect the source and drain when you have a positive voltage between gate and channel, right? Now, you can have a p-type, though, which is the opposite, where you basically just swap these, right? So, oh, sorry, that's only n-type. I'm only showing n-type, sorry. I don't show p-type? Okay. Yeah, I didn't just show p-type. So that's an n-type, right? But there's also a p-type, which is basically the opposite of that. So I'm surprised. I'm sorry. I thought I had a slide for the p. Yeah. So the PMOS is basically just the opposite of this, where you have p here and n here, right? And in that case, it works the same way, but you have to have a negative voltage. This has to be a negative voltage with respect to the body, right? Make sense? So in the case of digital logic, the NMOS is basically a positive logic in the sense that if the gate is 1, it turns on, right? Then there's a PMOS, which is basically the same structure but reverse the doping. This is a negative logic where if the gate is 0, it turns on, right? Now you might say, wait a minute, I thought you said it has to be negative. Yes, because in the PMOS, logic 0 actually creates a negative voltage on the gate because the body terminal of this guy is actually 1, is VDD. So this ends up creating, if you put a 0 here, you get a negative voltage. But for the purpose of digital logic, you just say this is a 0. You don't have a body. You don't have the body. It doesn't show the body terminal. It only shows 3 terminals here. So basically, a PMOS is if the gate is logic 0, right? If it's logic 0, it turns on. The NMOS, if it's logic 1, it turns on. And by turn on, I mean it connects. It electrically connects source and drain. And if it's not turned on, then it doesn't electrically connect source and drain. Right? They're not connected. In reality, they are. What it's really doing is creating a very high resistance if it's off and a very low resistance if it's on. That's what's really happening. But you think of it as on or off. Okay, so how does this relate to logic gates? So this part is, I remember the first time I saw this, I was kind of blown away by this. So first of all, in CMOS stands, so you know what MOS, I explained what MOS meant, metal oxide semiconductors. That's the sandwich that makes the gate, the insulator material, and the channel, right? Then if you say CMOS stands for complementary MOS. What that means is it's a style of logic where you use NMOS and PMOS transistors together to create the logic gate. The PMOS transistors are responsible for setting the output of the gate to 1. And the NMOS are responsible for setting it to 0. And you can only set the output to 1 at a time. You can only set it to 1 or to 0, not both, right? They're mutually exclusive. So the way you connect these transistors is that only one side or the other will be on at a time, right? That's why it's complementary. They're complementary in actually 2 ways. The first way they're complementary is one sets the output to 1 and the other one sets it to off. But they're also logically complementary in terms of the truth table. If you look at the truth table and you look at the rows of the truth table that give you a 1, right, versus the one that gives it the 0, the truth table rows that are 1 are the ones that activate the PMOSs, and the truth table rows that give a 0 activate the NMOS, right? So in other words, the PMOS is called the pull-up network, pulls the output up, and the NMOS is the pull-down network, it pulls the output down. And by pulling up and pulling down, what I really mean is basically just, you're not physically pulling anything, you're just shorting the output to ground, or you're shorting the output to VDD, right? That's by turning on the transistors on one side or the other. Does that make sense? Now you might say, well, why are the PMOS the pull up? And why is the NMOS the pull down? Why does it have to be that way? That's because the NMOS transistors are more efficient at pulling down. They pass zeros better, right? And the PMOS pass 1s better, right? Now the reason has to do with the fact that, remember I mentioned that in a PMOS transistor, it's not really a 0 that turns it on. It's actually a negative threshold, something less than negative 0.7 volts or something like that, right? How do you get negative? Well, that voltage on the gate is relative to the source, and the source is connected to VDD. That's why, right? In other words, what I'm trying to say is that because the PMOSs respond to a negative voltage, you have to get them up by VDD. And because the NMOSs respond to a positive voltage, you have to get them down to ground. Basically, that serves as their reference. Does that make sense? Okay, so the NMOSs are for pull down, the PMOSs are for pull up. Does that make sense? Okay, so the way you set this up is, if you want to make an inverter, inverter is the simplest gate because you have A, which is the input of the logic gate, and you have Y, which is the output of the logic gate. You take the input to the logic gate and you fan it out, meaning that you split it. You take the input to the logic gate and you connect it to the gate of both the PMOS and the NMOS, right? So it's fanned out. This is why, you know, well, I'll get into that in a minute. So you fan that out, right? But then the Y, which is the output of the gate, is connected to the middle of the two, right? So then, if A is a 0, it activates the top guy. Notice the bubble. You see the bubble up there, right? That bubble is there because it's a, you know, active low or negative logic, right? So if you put a 0 in for A, it activates that bubble, and it pulls Y up to VDD, right? Likewise, if you put a 1 in, it activates this guy, which doesn't have a bubble, positive logic, NMOS, and it pulls Y down to ground, right? So only either the PMOS at the top, you can think of it like PMOS positive, VDD, pull up, P. P is, think of it as positive voltage, right? NMOS, negative, ground, pulls down, right? So they're complementary, right? So only one of those guys is going to be on at a time. Make sense? Right? Now, you can extend this pretty easily into more complex gates. But this is the part that's, I think, is cool. So if you add another input, and so I have two inputs, A and B. So for each input, I have to have one transistor in the pull-up network and one transistor in the pull-down network. So if I have N inputs, I have two N transistors, right? But in this case, notice, just like the inverter, A goes to 2 gates, B goes to 2 gates. But the difference is that the PMOSs are in parallel, which means that you can pull the output up when only one of those PMOSs is turned on, right? But the NMOSs are in series, which means the only way to pull down is if both of those transistors are simultaneously on, right? So this way, if I put a 0, 0 in, then both of the pull-ups are going to be activated, right? So, and both of the pull-downs will be deactivated, right? But if I put a 1, 1 in, both of the pull-downs will be activated, and neither of the pull-ups will be activated, right? But if I have a 0 or a 1, or a 1, 0, then one of the pull-ups, one of the other of the pull-up resistors will be on, and one of the other pull-down transistors will be off, right? But I have to have both of those pull-downs because they're in series. They both have to be on, right? So the only way I can actually pull down is if I put a 1, 1 in, right? If I put in any other combination of inputs, then it's going to pull up, right? So this will create a NAND gate, right? Make sense? It's basically an AND gate, but it's opposite. And AND gate has to have 2 1s to be a high. This one has to be 2 1s to be a low. Okay? Now, there is an important limitation of this, though. What kind of sucks about CMOS is that if you look at the truth table, if you look at all the rows of the truth table where there's a 1, right? All the rows that give you a pull-up condition, right? I have to have at least one input as a 0 in order to achieve that. Make sense? Because in order to pull up, I have to have at least one transistor on. And the only transistors in the pull up are negative logic, right? So I have to have a 0. I have to have at least one 0 on at least one input. I need to have a 0 on at least one input for every row of the truth table that pulls up, right? Likewise, I have to have at least one on every row that pulls down to 0. Does it make sense? Did I say that right? So for all the rows that are outputting 1, I have to have at least one 0 in there, right? On the inputs. For all the rows where it pulls down, I have to have at least one 1. Does it make sense? Right? Now you might say, why are you mentioning this? Because you can't build an AND gate with this. Because AND gate, if you look at an AND gate, the only way you pull up is if you have a 1, 1, right? As the inputs. But you couldn't possibly build that gate. Because if you have a 1, 1 as your input, there's no way to activate any PMOSs, right? So you can't pull up. Likewise, you can't build an OR gate. Because an OR gate will only pull down on a 0, 0. But the 0, 0 will not possibly activate any NMOSs, right? So that's why CMOS logic is considered to be negative logic, because you can't build like an AND gate or an OR gate. Does that make sense? Right. Yeah. Exactly. Yeah. So you can add an inverter and create an effective AND gate, but you can't build a single structure. You can't build a single gate that's an AND gate in CMOS. It's impossible. Likewise, the buffer I showed you too, same thing. You can't build a buffer either. Okay, so here's a NOR gate. A NOR gate is kind of the reverse, where I put 3 NAND gates in parallel. This is a 3-input NOR gate. Why don't I have a 2-input NOR gate? Okay, well anyway, this is a 3-input NOR gate where I have 3 NAND gates are in parallel. These are in parallel, meaning if any of the inputs are 1, boom, you're pulling down, right? And then 3 PMOSs in series, which means in order to pull up, you got to have 0, 0, 0. You have to have all zeros to pull up, right? Make sense? Now, and keep in mind, these are complementary. There's no way to pull up and pull down simultaneously here. Because if I'm pulling up, then by logic, I can't be pulling down, right? Because they're the inputs, it's complementary. Okay. Yeah, so this question, I have example question. Which of the following Boolean functions can be realized with a single CMOS gate? So in this case, instead of giving you a single gate, I'm giving you like a Boolean logic. So not A and not B, not A or B, not A and B, A or not B. So to figure this out, you have to build a truth table for each one of those 4 options, as I did here, right? And then for each one of those, you have to make sure that if you're pulling up, you need to have at least one 0. So yeah, we're good here, right? If I'm pulling down, I have to have at least one 1. Okay, that works. Yeah, that works. That checks out, right? You go to number 2 and you say, okay, I need to have at least one 0 to pull up. I got zeros here, so I'm good there, right? Uh-oh, wait a minute. Wait a minute. This guy, right? 1, 1, right? I can't put 1, 1. I can't give it 1, 1 and have a 1 output, because the PMOSs are responsible for giving a 1 output, and PMOSs are not activated on 1, right? So this row doesn't work, actually, right? This one row disqualifies. This row is fine. That row's fine, and that row's fine, but there's one row of the truth table that makes it impossible to implement with CMOS, right? So that's basically how you solve that. Okay, there's also this thing called transmission gates. We talked about in Verilog the Z value in system Verilog, where Z stands for high impedance, and Z is when you have a tri-state buffer. When you can electrically disengage an output, that's how you implement that with a transmission gate, which is where you put an NMOS and a PMOS in parallel to one another, And the enable signal, which basically turns on the gate or turns off the gate, has to be connected to the NMOS and a negated version of that connected to the PMOS, or a complemented version, a not version of that connected to the PMOS. And so because the reason why you have to put two gates, as I mentioned, NMOS passes a 0 and a PMOS passes a 1. So in order to pass a 0 or a 1, you have to provide both options, right? And so that's a transmission gate, sometimes called a tri-state, or tri-state gate or tri-state buffer. Okay, any questions about that? Okay, so we'll come back to gates. I want to switch topics again and talk about power consumption. So I mentioned that silicon and CMOS is how all digital logic has been made for 60 years now. There are other semiconductor technologies, but there's a lot of them, but they can't compete in logic, mostly because the goal of digital logic is integration density, right? We want more and more transistors to make cool stuff, right? When it comes to digital logic, you want to maximize how many devices you have. So the problem is that those devices require power, and if you have billions of them, the power gets out of control really fast, right? Because each individual device is consuming power, right? It's already kind of out of control. Even on modern chips, they have this phenomenon called dark silicon, where if you were to try to utilize, like your desktop CPU, if you tried to utilize 100% of your desktop CPU, it would melt. It would go outside of its thermal envelope. It would have to throttle itself, and disable parts of the chip. You can't actually use your whole CPU. You buy a CPU from Intel, you can't even use the whole thing because it would be too hot, right? When it comes to CMOS, power is everything, right? That's the most important thing. It's even more important than performance because, as I mentioned, current mode logic, which is where you use current instead of voltage to represent a 0 or a 1, is actually faster than voltage mode logic. You can make a multiplier in current mode logic much faster than voltage mode logic, but current mode logic has higher power. So boom, disqualifies it, right? The old supercomputers of the 60s used to use current mode logic. The original Cray supercomputer used current mode because it's faster, but power efficiency is way more important than performance. So CMOS has two ways that it uses power: dynamic power consumption and static power consumption. Dynamic is from switching transistors, and static is dynamic power consumption happens only when you switch transistors from on to off or off to on. And static power consumption is constantly burning static power consumption. Yeah. So static, you can disable part of your chip by stop switching, right? That will stop it from using dynamic power, but it's still going to use static power unless you can power gate and actually shut the power supply off to that part of it. The only way to get rid of static is to power down the chip or part of the chip, right? Okay, so what is dynamic power consumption? I used to be under the mistaken impression that dynamic power consumption happened because when you switched a gate, like an inverter, right? I mentioned that when the input is 0, you're only pulling up or pulling down, right? And if the input is 1, you're doing the opposite, but you're never pulling up and pulling down at the same time. However, what about when you're switching from 0 to 1 or 1 to 0, right? Is it the case that you're shorting the pull up and the pull down networks temporarily in the transition that causes it to burn dynamic power? Is that true? No, it turns out I was wrong about that. That's actually not why, that's not the source of dynamic power. That's wrong. In reality, it's not a big deal. What's actually happening with dynamic power consumption is when you turn on a gate, or when you turn on an input to a gate, think of it as the input. you're charging a capacitor. The gate is a capacitor, right? You charge it. And then when you turn it off, you discharge it, right? Well, what happens when you discharge it? Where's the current go that you discharge? Does it get recycled back in somehow? Nope. It goes straight to the sink, straight to ground, right? Now, that said, there is research in regenerative logic circuits. There has been, that's been a holy grail for decades. People have been trying to figure out ways to recycle that power. When you go from 1 to 0 and you discharge the capacitor, can we get that? Can we recycle that back? Can we use it again? Or do we have to just dump it to ground and waste it? Well, that's how it works now. Maybe one day we'll have these circuits that we can recycle. But right now there's no recycling going on. So one way to think of this is when you turn on the gate, you charge the capacitor, and when you charge it, you spend power to charge it. When you discharge it, well, that's free, right? Now, you could think of it the other way and say, well, when you charge the gate, that's the free part because technically that charge is still available. It's like, potential energy. You actually don't spend any energy until you discharge it when you dump it all to ground. It doesn't matter which way you think of it. Either way, you only spend energy once. It's either when you're charging the capacitor or when you're discharging the capacitor, right? So for that reason, there's a 1/2, right? Now, how long does it take how much power does it take to charge a capacitor? It's CV squared. The capacitance times the voltage squared. That's to charge a capacitor one time with a voltage of V and a capacitance of C, right? So basically, the dynamic power consumption is 1/2. Why is it 1/2? Because you only pay once. CV squared, which is the power to charge one capacitor, times frequency, which is how fast you're switching, your switching frequency, right? How fast are you changing? How many bit flips do you have, right? So it's CV squared F times 1/2, right? Now, CV squared F, sorry. So the V squared, right, that's the important, so what does that V squared mean? That means that if I can drop the supply voltage, I get a tremendous savings in power, dynamic power, right? That's why there's a huge pressure to keep pushing that voltage down, 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 right? But we talked about the noise margin. What does that do to the noise margin? Well, the problem is as you push that voltage down, your noise margin gets thinner and thinner, and the likelihood of a transient error grows quite a bit, right? And the voltage threshold, the voltage that actually turns the diode on or the transistor on, is basically fixed. You can't, it really hasn't changed in decades. It's like 700 millivolts. It's changed slightly, but in silicon semiconductors, it's very hard to change the threshold voltage. That hasn't changed much, right? So basically, anyway, that's CV squared. V squared is, you can change the frequency, but that's only a linear relationship. The voltage is squared. Now, the capacitance, what controls the capacitance, by the way? Well, the smaller the transistor is, the smaller the plates of the capacitor are, right? So as you shrink the transistors down, the capacitance goes down and you become more power efficient. But the problem is if you shrink the capacitors, then you end up putting more capacitors on there, right? So then it makes no difference. So what that was called was Dennard scaling. If you ever heard that term, Dennard scaling. Dennard scaling meant that if the transistors were shrinking at the same rate that I was adding more transistors, then my power density would remain constant, which means I could go from 1 million transistors to 1 billion transistors and still have the same power density in terms of watts per area, right? So that was awesome, right? That basically meant I could create bigger chips without using more power. I could create more powerful processors, powerful in the sense of like computational performance, without spending any more power. That almost seemed too good to be true. Well, it was, because Dennard scaling ended about 10 years ago. That's no longer the case. The technology has changed, and the savings in capacitance now is now being outdriven by the increase in transistors. That's just the physics of the semiconductor. So there's no more Denard, there's no more free lunch. What about static power consumption? So that one is, static power consumption is also something that becomes more serious as you lower the supply voltage closer to the threshold. You get more leakage. So static power consumption is when current leaks from the power supply down through the pull-up network and down through the pull-down network constantly, right, across those channels. And basically that's just the quiescent supply current, which is the leakage current, multiplied by the voltage. So this is basically just power equals, voltage times current, right, which you learn in electrical engineering. What is the quiescent current? Well, that's basically, that's a function of the power supply and the semiconductor technology. But what this also means is that in this case, the voltage is not squared, which means that if I lower the supply voltage, it doesn't help me that much with static. As a matter of fact, it hurts me because the closer I get to the threshold, the more the transistors are sort of partially on, right? As opposed to being totally off. And I get worse supply current. So yeah, I save a lot of dynamic power, but I hurt myself on static power as I lower the voltage. Okay, so this is just an example here. I'll skip that. Okay, let's see here. How much time do I have? Okay, so let's skip that. I'll come back to that next lecture. Okay, so what about delay? We talked about delay in another lecture. We talked about contamination delay and propagation delay through gates. How does that manifest in these CMOS circuits? Well, so basically you have in this case, we split it out to rising propagation delay. So when you have a gate and the gate input goes from 0 to 1 and the output changes from 1 to 0, right? The propagation delay, like we didn't differentiate this in the previous lecture, but there's a rising delay, and this is measured generally from halfway. So halfway between 0 and the power supply, when you cross that on the input versus when you cross that on the output, there's a propagation delay. And that could be different for rising and falling. Now, if you just have one propagation delay, it's obviously going to be the worst of the, whatever the longest of the two is, right? And then there's rising and falling contamination delay. Okay, so what is that coming from? So I mentioned the capacitors. So every gate is a capacitor. It's designed to be a capacitor. It's literally what it's how it works. The problem is that capacitors take time to charge, and this is also what limits your speed. It causes delays, right? So every gate is a capacitor. The problem is that you also have other capacitors. So what is the gate? The gate is the input. So the gate is connected to the inputs of the gate. The gate of the transistor is connected to the inputs of the logic gate, right? However, the outputs of the logic gate, the thing that's actually pulling up and pulling down, that's the source and drain, right? And I mentioned that the source and drain create reverse biased diodes between the source and drain and the substrate. So in the case of a NMOS, the substrate is grounded and the source and drain are not grounded, right? And so there's a reverse bias. It causes no current to flow from the source and drain into the substrate. If it does, you're in big trouble. That's called latch up, and that'll fry your chip. Latch up is when you get current flowing from the source and drain down into the substrate, right? latch up can be the result of a badly designed chip. In the case of a PMOS, and I didn't show you this yet, but obviously the PMOS is different. But the problem is that when you make a chip, the whole chip has the same substrate. It's the wafer. You make a wafer, right? The wafer is the substrate of the chip. Generally, that's all PMOS, right? So how then can you how do you create a PMOS transistor? Well, you have to create a localized substrate for its source and drain, and that's called a well. So inside the substrate, you have a P substrate. You create a deep well that's N. You reverse dope it. And then inside that well, you create diffusion areas for the source and drain, right? So you create like a little local body terminal, bulk terminal for the transistor. But then, in order to reverse bias that, you have to connect the well to VDD, right? And this is why the gate voltage here is essentially negative voltage, right, for the PMOS. Because if you put a 0 on the gate, that's relative to these guys, which are positive. So that's like a negative VDD, basically, that you're putting for the gate voltage. Okay? And then this is called this little diffusion area here is the way that you actually get the well energized up to VDD. This is called a well contact. You create a little localized N plus, and the well is N. What's N plus versus N? N plus is highly doped. N is just lightly doped. But if you go from highly doped to lightly doped, it makes a real good connection, electrical connection. And then you connect that to VDD, right? So that way your well becomes energized with VDD, right? Your substrate is still grounded. So now there's a reverse biased diode between the substrate and the well and the diffusion areas, right? But here's the problem. Reverse bias diodes are also capacitors. Because remember that a capacitor is anytime you have two conductors separated by a dielectric. A reverse bias diode is essentially that, because the dielectric becomes the junction in the diode where the charge carriers are repelled from one another, right? So you have a diode. In a diode, the junction, when you try to reverse bias a diode, the junction partially becomes kind of an insulator, and you end up with a capacitor. So the problem is that not only is the gate a capacitor, but both the source and drain are also capacitors, right? So you have capacitance on the input of your logic gate, and you've got capacitance on the output of the logic gate. You get a double whammy, right? You have to charge the input, and then you have to charge or discharge the input, and then you have to charge or discharge the output as well. So that pull-up or pull-down network also is a big capacitor, basically. And that's called, they call that parasitic capacitance. So I mentioned this earlier to you guys in the semester, but gate delay is caused by resistance times capacitance. So the time it takes to charge a capacitor is the resistance times the capacitance. Very simple. Just like the power is capacitance times voltage squared, the delay is resistance times capacitance. So you can model the delay of a transistor using this thing called the RC delay model. And the idea is that if, let's say I have an NMOS transistor, the gate is connected to a capacitor ground, right? Why? Well, because the substrate is grounded, right? The channel, right? Likewise, on a PMOS, it's the same thing, but there's capacitors to VDD on the gate, right? You guys with me? So that's the gate capacitance. Then the source and the drain are also connected to capacitors, in this case to ground, on the NMOS. Why? Because the substrate is grounded. But over here on the PMOS, they're connected to a capacitor to VDD, because in a PMOS, the substrate is VDD'd, is power supply, charged up, right? Make sense? Okay, and also the transistor itself, I mentioned this earlier, is a resistor, right? Why? Because, well, it's a semiconductor. So when the transistor is turned on, it still has resistance. There's still resistance across the channel. It's a small resistance, and it gets smaller the smaller the channel is, but it's still a resistor, right? So that's where your RC delay comes from. It's the resistance of the on capacitor multiplied by the capacitance, right? Now, the problem here is that it's a little complicated because if you create a gate, let's say I have an inverter driving an inverter. This first inverter has two capacitors for the source and drain, right? But check this out. The source, which is the bottom terminal, is connected to ground, but its capacitor is also connected to ground. So this capacitor actually doesn't count because you're guaranteed that both sides of this capacitor are just grounded, so it doesn't affect your delay. The only capacitor here that affects you on this NMOS is the drain capacitor, because it's the one that's connected to the output of the gate and it goes to ground. So you only have to count this guy. Does it make sense? You don't count the source capacitor, only the drain capacitor. Likewise, on the pull-up, this capacitor on the source of this guy is connected to VDD, but the source is also connected to VDD, right? So this capacitor doesn't count, only this one does. You guys with me? So basically, I just have 3C. Now you might say, why is that top one multiplied by 2? I'll come back to that in a minute. But basically, you're only affected by that. And then you connect to the input of the second guy, this guy, and this guy has gate capacitance, right? So basically, if I'm looking at the delay here, I have to count the source and drain capacitance of the driving inverter and the gate capacitance of the receiving inverter, right? So you add all that capacitance up. So in this case, it becomes 3C plus 3C is 6C, right? C being the unit capacitance. And then the resistance is whatever the resistance of the effective resistance of the transistor. So this is 6CR is a delay of this guy. You guys, does that make sense? So this is the way that you can calculate the delay. Now, if you change the size of these transistors, I haven't talked about the sizing of the transistors, that changes things. This is a minimal size, okay? But anyway, I'll finish this after Thanksgiving.